Hello everyone. Today we are going to talk about Taylor series and Maclaurin series. And I'm sure you have seen these two topics in your calculus course, but may wonder where you would use any of these series in real life, correct? So you know that, for example, if I have a function f of x, then I can expand it as a summation of polynomials, infinite number of them, around the specific point, point A, which we call the expansion point. So I can say that f of x is equal to basically f at A, which is a constant number, plus f prime at A times x minus a over 1 factorial plus f double prime at a times x minus a squared over 2 factorial. You see, so this is the constant, this is the linear polynomial, this is the quadratic polynomial, and keep going. Right, now it's going to be the third derivative of a times x minus a cubed over 3 factorial, and you keep going. The general term would be the nth derivative of function f calculated at a times x minus a to the power n over n factorial, and you keep going. So you can basically calculate your function by an infinite series. Well, first question that comes to your mind is, I can never keep adding stuff until what? Until infinity. It's not going to happen, okay? You have to stop at some point. And when you stop at some point, then this is not going to be an equality. It is going to be an approximation, correct? So if you stop at some term, when this small n equal to specific number, then that is going to be what? That is going to be approximation. So for example, here, let me add another example of that for you here. Okay, so let's say I only go until small n equal to something, let's say equal to capital N. So, or m or whatever, right? So let's say I use m terms. So like this. And this is not going to be equality anymore. This is going to be what? Approximation. Again, we call point A to be what? The expansion point, and m to be the number of terms used. Okay, and this is an approximation. It has some error in it because we didn't go forever. But that's what we can do in real life, to stop at some point. Good. So first of all, we cannot add forever. Second of all, what's wrong with the function itself that instead of the function you have to use a bunch of polynomials to approximate the function? Why can't we use the function itself directly, right? For example, if you use this Taylor series for function sine of x, so here, for example, you say sine of x is approximated by x minus x cubed over 6 plus x to the 5 over 120, and keep going. Or you might stop here. You say when this cap m equals 5, I'm gonna stop. Okay, so why should I do this? Why should I approximate my sine function by a fifth order polynomial? Why can't I directly use function sine of x? Right? Why should I do that? What's the point? And that's where they typically stop in a math class, and they get into proofs and radius of convergence and everything, they don't mention why you should approximate your function with a bunch of polynomials. Why would you do that? What's the application in real life? And I tell you here one motivating application that hopefully makes this topic a little bit more interesting to you. And that is in your calculator, right? When you have your calculator, and in your calculator you have what? You have a sine function, correct? And then you type in some number, any number that you want, correct, in degrees or radians. So let's say here you type in, for example, what? 25 degrees or 25.6 degrees. And then you click on sine to calculate sine of this angle, right? Or cosine of the angle, or logarithm of the angle, and so on and so forth. How do you think your calculator is calculating that? Correct? So you have all these functions. How do you think your calculator calculates all of these numbers? Let's say, for example, sine. Well, we know sine of specific angles, right? Sine of 0, sine of 30, 45, right? 60, 90, maybe 36 degrees, 180, 270, and so on. But when you type in any angle with any number of decimals, or maybe even no decimals, how do you think your calculator calculates that? It does not have a lookup table with every single angle, right? Where here is x, here is sine of x. And in that table, any number that you can imagine is on the left side and their sign is on the right side. So it goes, looks up and type the number for you here. There is no such possibility, right? Because there are infinite number of angles you can enter. And if it does interpolation, you might say, well, 25 degrees is probably close to 30 degrees. So it tries to interpolate between 30 degrees and let's say an angle smaller than 25, and probably the next angle you know very well is 0, right? So you say between 0 and 30 lies 25, so it approximates between them. Well, you cannot do that. Your sine function does not act like a linear or quadratic function between 0 to 30 degrees, so you can do a nice interpolation. And if you do, the number is going to be rather horrible. Okay, right? So sine of 0 is 0, sine of 30 is 1/2. So if you do a linear approximation, let's do it here. So it is going to be 25.6 divided by 30, correct? Or divided by 30 minus 0. And this is going to be 25.6 minus 0. And then the whole thing times 0.5 minus 0, correct? And so sine of that, if you do linear interpolation, is going to be 0.467, while if you calculate sine of that angle, you see, it's not even accurate to the second decimal. So an interpolation is not going to be really a good choice. And you might say, well, that was only 0.01 of a difference. Yes, but remember, sine function itself cannot go more than 1, right? So it's not really a small error. And for some applications, you really need to be very accurate. You cannot afford the 1%, 2% error, 5% error. So especially for a simple task like calculating the sine of an angle. And in that case, as I said, it wasn't too horrible because 25 degrees was close to 30 degrees. Okay, if you increase the range, and this is somewhere mid-range or so, that linear interpolation is going to be even more horrible. So that's not how your calculator calculates that. Doesn't have an infinite lookup table, doesn't do interpolation because it has a lot of error. So the way it calculates sine, cosine, tangent, exponential, logarithm, or other functions for any specific number that you type in, arbitrary number, they use the Taylor series. Really? Yes. So here, this is the Taylor, or you might call it Maclaurin series of the function sine of x. By the way, we call these the Taylor series. So let me mention that. So this is the Taylor series. When you expand it about an arbitrary expansion point x equal a, but when a equals 0, so you expand it about origin, instead of Taylor series, you call it what? So here a is arbitrary. But if you make a to be 0, then you would call it what? You would call it Maclaurin series. Okay? So here it's expanded about 0. So this is the Maclaurin series of function sine of x. And I can show you, although you are doing approximation and only using 6 terms here, basically because there is a constant term, so it's like 6 terms here, 3 of them are 0. This is enough to give you a very good approximation of the function sine of x. So if you just use this is going to be rather very good approximation of the function sine of x for a wide range of angles. And if you want more accurate, then you add one more term, which looks like x to the 7 over 7 factorial. Okay, but this is a very good approximation. Now, to demonstrate that, I'll use a known angle for which we know sine specifically. So I would use 30 degrees in this case. And we know sine of it should be 1/2, so we want to calculate this number and see whether this number is also 1/2 or not. Okay, so what do? We define that function. We say f of x is equal to, at sine of x, I'm using anonymous function, it's x minus x cubed over 6 plus x to the 5 over 1/n. Okay, and now what is x? X is 30 degrees. Now make sure you do not pass 30 here to x. When you are expanding it this way, you are expanding x. X is in radians for a harmonic function. So make sure you have to first convert this guy into radians. So say x is what? Pi over 6. Then pass it to the function. Okay, never pass it in degrees. So x, I say, is pi over 6. So I say calculate f at what? Pi over 6. Look at the number. How much? Exactly 1/2. Now, it's not exactly 1/2. You see exactly 1/2 because you are only showing 4 decimals. If you want to see it with more decimals in MATLAB, use the command format long. And now do it again. You see, it's not exactly half, but if you look up to 5 decimals, it is 1/2. It's only after 6 decimal that you see a difference. Okay, so if you say, what is sine of pi over 6? You see, it gives you perfectly half. Doesn't give you this. So what is MATLAB doing? How can MATLAB get rid of all the zeros? Well, that's because MATLAB is using more terms. MATLAB is not just going to use up to x to the 5. It's going to probably go higher powers. And the more power you use, of course, you do a little bit more calculation, but you get better error, right? So here, for instance, I add one more term to my calculations. Okay, so I use the function factorial. And so this is my function. And now I do it again. Now look. If you see here, now if you round it, correct? If you round it, all of this is going to be 50. And now you have accuracy to 8 decimals instead of what? Instead of last time that you had 5 decimals. If you want to get even better, add one more term, and this time you have to add x to the 9 over factorial of 9. Now look. How many? Yes, 10 decimals. You got up to 10 decimals accurate. Last time it was only what? 5 decimals. Now it's 10 decimals. So you predict probably if you add 2 more terms here, that would give you probably these guys also gone. So all you need is probably add a little bit more, and I add more. So I say this is going to be negative x to the 11 over factorial of 11, and then plus x to the 13 divided by factorial of 13. And now I do it again. Look, you see? Perfect to 15 decimals. And that's where MATLAB stops. So whenever you call MATLAB, the function that MATLAB uses to calculate your sine function is this guy here. Okay, this is what MATLAB uses. How far does it go, basically, MATLAB? It is based on the definition of epsilon in MATLAB. EPS, sorry. EPS in MATLAB is this number. It's 2.22 e to the negative 16. For MATLAB, any number below this practically means 0. I mean, when it adds two number, okay, if the addition of two numbers is, let's say, 10 plus 2 point this number plus epsilon, for MATLAB, 10 plus epsilon is equal to what? 10. MATLAB cannot do more because the memory it uses to store the numbers does not allow it to go more than 16 decimals. When it goes to 17 and 18 decimals, MATLAB cannot keep track of the numbers. And so practically when it does arithmetic, any number below this for MATLAB means what? And you can see here, let me add 10 plus epsilon. You see, it's 10. And remember, I'm using format long here. So if it had more decimals, it would show it for me. But you see here, it didn't. So when I add epsilon to 10, it is 10. So epsilon or numbers less than epsilon in MATLAB are 0. And you see it's what? It's from 16 decimal and down. So that's why MATLAB uses 15 decimals. And as long as your number to 15 decimals is accurate, then from that point onward, MATLAB doesn't care. And for sine function, they determine that if you go until 13 factorial, that would give you 15 number of decimals correct, and that's enough for MATLAB. Okay? Or the cosine function, for example. What's the cosine of a specific angle? How do you think MATLAB does cosine? The same thing. So if you go to cosine of x, if you look at cosine of x, so cosine of x, the Maclaurin series for it is 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial and plus dot dot dot. Okay, so you can stop it at some point and say, well, I want to only use the first 3 terms, and I'm going to what? Approximate this. Now, is that accurate? Probably up to some point, but of course you need to add more terms, right? And I can try it for you. So this time we're going to try it on function cosine, and we're going to use 60 degrees because cosine of 60 is also 1/2, right? So here I define a function g, and I say, well, I can define g similar to f, but with fewer terms. So it is going to be 1 minus x squared over 2 plus x to the 4 over 4 factorial, which is 24, and then minus x to the 6 over 6 factorial plus x to the 8 over 8 factorial, and so on and so forth, right? If you want, I can go further. So this is going to be 10 over 10 factorial, and then plus 12 over 12 factorial. Now, whether that's enough or not, we'll find out. So that is a function g, and now I calculate my g at 60 degrees, which is pi over 3. And you see, it does not go perfectly up to 16 decimals because I stopped at term 12. I need to add term 14 to make it accurate, but if you can see clearly up to 10 decimals, it is 1/2, which it should be. So all I need is to go here and add the 14th term. Now if I calculate it, there we go. I'm way better, right? And if it's not still enough, you add one more term, and that is x to the 16 over factorial of 16. And you see, now it's perfect, up to 15 decimals. So you clearly see how MATLAB calculates your functions. Or when you have, for example, exponential function, right? Exponential function is simply 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus all the way x to the n over n factorial, and keep going, right? So if I stop at some term, I can approximate it. And that's what MATLAB does when it calculates exponential of some number, right? So for example, you know exponential of 1, correct? The Euler number is 2.71828, right? That's the Euler number, correct? And no problem. But when you say what is exponential of 1.2, right? Well, how does MATLAB calculate that? Because you might know the Euler number, but what about something different, right? So this is Euler number to the power 1.2. You don't have a lookup table for it, so what you do is you plug in this 1.2 in the function that is like h equal at sine of x, and then 1 plus x squared over 2 plus x cubed over 6 plus x to the 4 over 24 plus x to the 5 over 120. These are the factorials I'm calculating, right? And all I need is to pass to the h function 0.1.2. You see, this is that, and this is what MATLAB gave me. You see, rather close, not perfect. I only actually have 1 decimal. I have some error here, and that's because I stopped soon. I need to add what? A bunch of more terms. So I need to go x to the 6 over factorial of 6, which is 720, plus x to the 7 over 7 factorial, which is, and just directly type it. Right, so now if I do it, should be closer to this. You see now, if you look, these numbers are very close, and I can add probably a few more terms. X to the 8 divided by factorial of 8 plus x to the 9 over factorial of 9. Now I should get a lot better numbers. And you see now it is up to 5 decimals, correct? Okay, so how many terms do you need? It depends on the function, how fast the function is changing, okay? The faster the function is changing, and also depends on the specific points. So they are not deciding the number of terms for one space on one single point. Basically, they need to make sure that for a range of data points, the error is below what they need, probably below epsilon in this case, and then based on that, they decide when they write their software or when they make their calculators how many terms for each function they have to use. Okay, so it's not the same number of terms for each one of these functions, and that depends on the function, as I said. And they choose it such that for any point, any range of point numbers that you enter, the error is always below some threshold. So hopefully now you learned that these Taylor or Maclaurin series are what's making your calculator or your MATLAB or any other calculating device for these functions work, okay? Because they don't have a lookup table, they cannot do interpolation. That's how they work. Plus, if you know about digital circuits and how the computers are made, basically the circuits, the ICs in computers are capable of basic operations, okay? Adding, subtracting, at most multiplying, and so on, right? Depending on how expensive of chips you're using in them. There is no chip in your computer for doing a sine function, okay? You can basically just add numbers. If you want to do multiplication, if you have a specialized chip, it can do it. Otherwise, for multiplication, it just adds the number together a specific number of times, right? If you want to raise power, it just multiplies a specific number of times and so on. So that's how the computers are made and how the chips are working. So anyways, hopefully this is clean for you now and why you learn this topic in your math. Now, one last thing before we go, and that is called the radius of convergence. So here I wrote this expansion for sine or cosine or exponential or any other function. And this x here that you have, can it be any x that you want? I mean, when you expand it around a specific point A, does that work for any arbitrary x, or there is some limitation how far from A this function approximation is accurate? And that's what's called radius of convergence, okay? For example, if you do a Taylor series or Maclaurin series over function 1 over 1 minus x, it is going to be 1 and then plus x squared plus x cubed plus x to the 4 and so on. Okay, now you might say, well, is this going to work for any x? Well, we'll find out. So here, I just give you one very simple example. Can I use x of 2 here? Just guess. If I use x of 2 here, does this formula work? So if I plug in 2 here for you, what would happen? This number is going to be 1 over 1 minus 2, which is negative 1. This is definitely going to be a positive number because every term is positive. How can negative 1 be equal to a positive number? Clearly, it's not going to work, right? Yes? You clearly can see that. True? Or let's say let's use a specific number of terms here and approximate it for another point. So let's say I use what? I use up to x to the 5. Now, what if I use negative 2? So here, instead of 2, I use negative 2. What happens? If I use negative 2, this is going to be what? 1 over 1 minus negative 2, so it's 1/3. And here, if you plug in, you know, this is negative 2, this is 4, this is negative 8, this is 16, this is negative 32. Clearly, if you add these numbers together, it is going to be negative, right? Just add them. This is negative 42, that is 21, so it is going to be negative 21. And 1/3 is, of course, very, very different from negative 21. So you see clearly this formula did not work for negative 2 or positive 2 and so on. And in this case, you can show this formula that I wrote only works when x is between negative 1 to 1. When x is between negative to 1 to 1, then this function can be rather accurate. And I'll show you very fast here. So I had function h, now I use another function, maybe function q. And I use only 5 terms. So here we go. right? Now I calculate this as 0.5. That's the number. And then what is 1 over 1 minus 0.5? Correct? You see, they are very close. And if I want, I can make it more accurate. I add some more terms. So here, x to the 6 plus x to the 7, right? I add 2 more terms, calculate it one more time. You see now, it's even getting closer. Last time it was 1.968, now it's 1.992. It's getting closer and closer to 2. If you want, you add a few more terms. And now if you do it, you see the difference is 1 over 1,000. And you're getting there clearly, right? But again, if I do it at a number outside the range, it's not going to work. So look, for negative also 0.5, that's the number. Now if you do it for negative 0.5, that's what you should get. And you clearly can see these two numbers are very close. Again, up to 3 decimals, they are the same. So this approximation only works for x negative 1 to 1. Now, how do I know that? How can I determine that? So that's the discussion we call radius of convergence. So let's very fast discuss that. So the radius of convergence says if you approximate your function f of x, and this is equal to, as you know, it is equal to f of a plus f prime of a over, let me use a k here, so over 1 factorial x minus a to the 1 plus f double prime a x minus a squared over 2 factorial plus dot 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 plus the kth term. So in here I use k instead of n. The kth derivative at a times x minus a to the k and over k factorial, and keep going. So here, if you name these terms, each one of these terms, give them some name. So for example, this term, you call it whatever you want. You call this term, for example, term bk, okay? And the term that comes after it, which is basically, if I want to write it, it is going to be fk1 derivative at a x minus a to the k plus 1 over k plus 1 factorial, and keep going. So if I call this guy b of k plus 1, the convergence theorem for the Taylor series says that this series will converge to the function at any point if the limit of bk plus 1 over bk, as k gets bigger and bigger, is always less than 1. So your terms are getting smaller and smaller, then of course you can treat it like some kind of geometric progression, that the terms are getting smaller and smaller and it will converge. If the terms are getting bigger and bigger as k gets bigger, then you will not have any convergence, okay? So here, if for example I tried for this 1 over 1 minus x, clearly you see the k term is x to the k plus 1 term is x to the k plus 1. So for that function, it is going to be the limit of x to the k plus 1 over xk has to be less than 1. And clearly, if you simplify, it is going to be that the limit of x has to be less than 1 for any k, and that means x has to be less than 1, okay, in magnitude. Because here this limit does not have anything to do with k. So the condition here is absolute value of x has to be less than 1, or x is between -1 to 1 for the convergence. But for the sine function, for example, if you go back and look at the sine function, here, if you look at this limit of bk plus 1 over bk, so bk plus 1 over bk, if you look at it, bk plus 1 is x to the now you have to pay attention that one term and the next term, one of them is always 0. So in this case, if bk is x to the x minus a, which in this case a is 0, so x to the k, right? And then the kth derivative of the sine function, right? And then divided by, so it's either a positive 1 or a negative 1, right? And then divided by the k factorial. So it's either positive 1 or negative 1 because it's the kth derivative of the sine function, which has to be either, and k has to be an odd number here. Then it is either positive sign or negative sign, and at 0 it's either, since it's an odd derivative, it has to be either cosine or negative cosine. And at 0 it's either positive 1 or negative 1. But the next term, that is going to be an even number, this guy is going to be 0. You see, for example, if k is 5, the k plus 1, which is x to the 6, the term for that is 0. If k is 7, the next term 8, k for the coefficient term, the whole coefficient for that is 0. So this limit is going to be 0, and this 0 is always less than 1 regardless of how much x is. Okay, so it does not care where your x is. This limit is always 0. Therefore, for what range of x this sine function and its Taylor series are showing the same number for any x. Okay, any real number, this sine function is going to work. There is no limitation. You can show the same thing for cosine or exponential. But not every function will, the Taylor series for it will converge to the actual function for any x value. Some functions, they have some limitation. Okay, so I guess I have covered this topic, and hopefully I motivated you why you learned this topic in your math classes and where you would see that in real life along with the limitations and everything. So thank you so much. I'll see you in the next lecture.